So suppose let's take x is any distribution. Suppose let's take our x is any distribution. Okay, so if this is any distributions, now we will see how the sampling distributions are actually work in central limit theorem. In short, we will called central limit theorem, CLT. So this is the central limit theorem is the main primary and beautiful idea in the probability and statistics. Not only probability statistics, it's the beautiful and most important idea in the whole of mathematics. Suppose let's see these things step by step. Suppose let's take and x is our any distributions. Suppose as an examples we will take for it will be better if we taken instead of taken any distributions, if we taken an example of this. Suppose let's take our distributions is x is any distributions, and let's take as an example is then the distributions of incomes of the people is the simple distributions of incomes of people. Okay, let's take. So suppose let's take it's PDF. Its PDF are actually look like this. Let's take, because it is any distributions. Suppose let's take its PDF is look like that. So because it is an any distribution, suppose let's take. So it is not necessarily it is a Gaussian distribution. Not necessarily it is a Gaussian distribution. Simple, these things are any distributions. Now first thing that we have to do from these distributions, we have to collect the samples. And one of our previous lectures we have shown how to build the sampling, how to collect the sampling from a populations. And the thing that we have to remember, that distributions is the population distributions of the x. These things is the population distribution of the random variable x. Okay, so first we have to take on the first step that we have to take. We have to collect the random sample from these populations. Okay, so first that we have to collect the random sample. Random samples of suppose of size n. Suppose let's take the size is n. Suppose let's take, for better understanding, let's take let it the size is equals to n is equals to 30. Let suppose it's first we have to collect these things. Yeah, and let these things are h1, that samples we have take collect randomly s1 and s1. Suppose let first collect the samples, and we have collecting such kind of m samples. Similarly, first we have doing this job. Secondly, also again repeating, we have collected the random sample of same kind, and let these samples is s2, and we are doing these jobs such kind of m times. We are doing this just m times. First we have to calculate its mean for each sample. This is the sample 1, then we have to calculate its means. Suppose let's take its mean is x1 bar. Now in second we have to calculate its mean. Suppose let's take its mean is x2 bar. Similarly we have to calculate also its mean. Suppose let's take xm bar, its mean is. So these things, this that don't be confused, this is the sample and this is the sample mean. Okay, this is the sample mean, this is the sample, this is the sample from x and this is the sample mean. Okay, that's thing that we have to do in this job. So what, that first we have collecting such m samples whose mean is x1 bar, x2 bar, x3 bar, xm bar. This is the sample m sample means. This is the sample m sample means. Okay, now the question is, the big question is the what kind of distribution these samples means are follows. Suppose let's take the sample means that xi bars, the sample mean the xi bars are obey some or follow some distribution Now let's take, so just don't view this sample, these things are distributions of, these things are distributions of sample means. These things are sample distributions of the sample means. Yeah. So don't be confused about this term. So the distributions of xi bars are, these things are the sample, the dissampling distribution. These things are called the means. These are the sample mean and I am taking the distributions of the sample mean. Okay, I am taking the distributions of the sample mean. So these things are called the sampling distributions. Because of this, these things are called the sampling distribution. These things are called the sampling distributions of what? Of sample means. These things are sample mean. Sampling distributions of the sample mean. Because of this region, this is the sample mean and these distributions is the sampling distribution. Okay, because of these two reasons, these things. Now the big question is, what kind of distribution this sampling means are follows. So the question is, what kind of distribution x bars follow. This is the big questions. So to get this answer, to get the answer of these questions, the central limit theorem comes into the pictures. Okay, to get the answer of these questions, the central limit theorem comes into our picture. So now let's discuss step by step the central limit theorem. What is actually central limit theorem? Okay, so let's discuss it. Okay, central limit theorem. Let's discuss. So let x be any distribution. First let let x be any distributions, and obviously it is any distributions, and obviously it will have a finite mean and variance of its populations. Okay, and the first conditions that I have to take, that x that this x must have a finite population mean mu and variance sigma square. That's the first conditions. It must be finite, and obviously finite, and its populations mean and the variance and the populations mean and its population variance must be finite. This is the first conditions that we have to. Also there have some distributions that have infinite mean and variances. Suppose let's take, there have some distributions that has infinite mean and also variance. So these distributions are Pareto distributions. We will see these things, Pareto distributions, in the next lecture. Now just bear with me. So the in Pareto distributions, its mean and variance are infinite. Okay, but here in central limit theorem is applicable only the distributions that have finite populations mean and finite population variance. So first assumption is. The second assumptions is, second things that we have to do, that second thing we have to collect the samples from this distribution. So in the second step that we have to do, we have to collect the samples from these distributions. We have to collect the samples. Suppose let's take, we have collected such kind of m samples. So first sample is 1, second is S2, third is S3. We have collected such kind of m samples of size n, and that we have to remember h samples that we collected, the samples of size n. Samples of size n, that we have to remember this thing. And the mean, and then we have to calculate the mean of its h samples. Suppose let's take its mean is x1 bar, its mean is x2 bar, its mean is x3 bar, similarly its mean is xm bar. Okay, so this is the sample mean, this is the sample and of size n, and this is the sample mean. Okay, now we are interested to find its distributions. So its distributions of these xi's is the simple, these things that we have called the sampling distributions of the sample mean, that we have to find the sampling distributions of sample mean. Sampling distributions of That's thing we have to, that sampling distributions of the sample means that we have to calculate, it. And to calculate this thing, the central limit theorems comes into the picture. So central limit theorem says that the central limit theorem says that the x distributions of the xi bars that follows the normal distributions of this sample means, are follows the normal distributions with mean mu, means these means are the population's mean of the of our distributions. This mu and this mu are the same mu, and its variance will be sigma square by n. This mu is the sample, the population mean. This mu are the same as the this mean, and this sigma square are the same as the this sigma square, mean populations variances. So I think it will be better if we just, this mean and the this mean are the both are the same thing, both are the same thing, and these variance and these variance both are the same, both are the same variance. Okay, that's the thing that the central limit theorem are, and the conditions is h n tends to infinity. This is the first one, this is the condition, h n tends to infinity. Okay, as we increase the sample size, then the sample mean obeys this rule, these distributions as correctly. Okay, this is the thing that central limit theorem says us, and this n is that also, well, and already we have know this n is simple the Gaussian distribution. Gaussian distribution. I think you have understand the Gaussian distributions is how much important. If we have any kind of distributions that we have no any behavior of these distributions, just only known its population mean and variance, by simple sum collections of its sample from these distributions, we can easily calculate its some kind of characteristics behavior, because from this beautiful and most elegant theorem, central limit theorem. I think you have understand, and it will be better if I take an example to discuss this thing. Suppose let's take we have taken an example. As an example, I have taken an x is a random variable of the incomes of the people, is a random variable of incomes of people. Okay, we have collected, and this random variable, in this random variable there have finite population mean, mu, and variance sigma square. We have these things for these populations, and these distributions a this random variable x, it follows any distribution that it's need not be a Gaussian distribution. Okay, it follows any distributions. And suppose let's take as an example, I have taken this random variable of these the sample, the incomes of the people, and its finite mean, it's finite in these populations, it have finite population mean, and finite population variances. That's the first condition. First, that we have to doing the job, first we have to collect its samples. Suppose let's take, we have collect its 1000 samples, x1, x2, x thousands. So in the second thing that we have such kind of 1000 samples, let's is equals, we have collected such kind of 1000 samples from this random variable, the infinite, that's the random variable income of the people, incomes of people. and its samples are size n. Its sam- its sample, it size of this I is equals to 30. Okay, we have collected such kind of 1,000 samples, and its size of the age is 30. So how much total point we have collected? We have collected 100 samples, and sample is 30. We have collected 30k such samples. Okay, we have collected 30k such samples. And next that thing we have to calculate it. The mean of the calculated one calculated is 2, that we have calculated the mean of the sum. Okay, sorry, it will be, we have calculated the mean of the sum. The sample means of income of income of its sample, that we have calculated. Okay. Now, if we just plot these things, we just plot now after the calculated. If you plot this data, the samples, 1,000 samples, mean of the 1,000 samples, or the mean of these samples, then you will come, then you will find this kind of Gaussian kind of, and this Gaussian. And the central limit theorem says that this Gaussian, the mean of the Gaussian graph, mu is a sample same mean of this mu, its distributions and its deviations or its rate in sigma square. These things are shared is the central limit, is the sampling distribution. The things are the sampling distribution. Sampling distributions of the sample means. Okay, these things, and that things are actually this mu approximately equals to mean, means the mean of the distributions, the mean of the these things, this mu means of, is the distributions of the mean of the sample mean of the sample means, they are the sample mean, and the mean of this means same as the these things are called by, these things are said central limit, and sigma square by n equals to variance of the, okay, that's things, the central limit, that's things are actually, I think you have understand the main concept, how these things, how the central limit theorems are comes into the picture, why these things, without knowing anything of our distribution, and we can assume some properties about, if a data set, if I collected some data sets, we don't know the correct, don't know any distribution, just we don't know distribution mean and its variances, you know, that's just two things of that populations, we don't know any kind of distribution, oceans or any kind, maybe any kind, by simple collecting some samples from that, from that distributions, from that set, that data set, and easily we can easily draw some we can easily conclude some kind of we can easily take some kind of conclusions of that by using this beautiful and most elegant central limit. I think you have understands its beauty, its importance, and also using these examples that come out with clarity of central limit. And in the next part of the lectures, we will see how much it is and why, when, where we have applied these theories. We will see this thing.